Hello, Ms. Nicole and fellow peermates. We are Group 9 and we will be showcasing our research study on the prediction of medical insurance premiums using machine learning models and data analysis techniques. The problem statement begins with the challenge of determining medical insurance premiums that are priced fairly for both insurance companies and individuals. Medical insurances help to offset healthcare related expenses, where individuals pay premiums to keep their plans active. Arising factors in our modern day-to-day lives contribute to the complexity of ensuring prices are accurate, honest, and justifiable for everyone. Our key research goal is to develop a reliable machine learning model that accurately predicts medical insurance prices using machine learning techniques and methodologies along with data analytics. This in turn helps to give peace of mind to customers while insurance companies can maintain a competitive edge in the industry and provide insightful data and patterns to healthcare companies. Throughout this research, our objectives are to inspect the quality of the dataset and understand its key features, conduct exploratory data analysis to clean and comprehend the dataset, identify the factors that affect medical insurance prices the most to help with feature engineering, discover optimal pre-processing, feature engineering, and hyperparameter techniques for fine-tuning the predictive models, assess the performance of various models using evaluation metrics and validation techniques, explore, evaluate, and identify the best performing machine learning model for the prediction of medical insurance prices to be used in the real world.
Now we will look at the related studies involving our study. These are four sources which we have found which have done a study in a similar topic. According to their varying data pre-processing techniques, Panda identified and handled missing values by inputting means, while Abalawi used a min-max scaler to transform the features. All four sources have used either label, one-hot, or dummy encoding for their categorical features. Furthermore, Kokani and Albalawi use feature selection or engineering to determine the best categories to be examined in their study. Finally, sources 1 to 3 split their data into an 80-20 or 75-25 ratio for a regular trained test set, while Fulton Reuter used grid search CV to determine the best parameters for their models. For the methodology, Panda used an empirical study of extended linear regression models, while Albalawi used multiple machine learning models for accuracy. Meanwhile, Kulkarni used multiple regression models, while Fulton Reuter did the same based on R-squared score, root mean squared error, and computational time.
So now I'll be presenting the machine learning models and their evaluation matrix. So in the first study done by Panda and colleagues, they explore several regression models such as simple linear regression, multilinear regression, polynomial, rich regression, and lasso regression. So a key highlight from their finding was that polynomial regression achieved the highest accuracy score with an R square score of zero point 0.8 and root mean square score of 5100.53. So moving on to the second study by Kulkarni and colleagues, their study utilized linear regression, decision tree, gradient boosting models, and notably, gradient boosting displayed outstanding performance with an R-square score of 0.87. Okay, so now moving on to the third study by Fusen, Reuter, and colleagues. So their study evaluated multiple models such as linear regression, KNN, support vector regression, simple decision, random forests, and XGBoost. So notably, XGBoost achieved the highest R-square score of 0.89, and in terms of computational efficiency, simple decision tree had the fastest computational time at 0.26 compared to 39.2 seconds for random forest. Then next, for our fourth study, they carried out extensive pre-processing using min-max scalar and dummy encoding. And for visualization, they used line chart, scatter plot, histogram, and box plot to understand the spread of the dataset. And through feature engineering, they identified and removed the region feature due to its low impact and perform a train test split to optimize the model's performance. Okay, so now I will talk about the gap analysis. So question one, which model fares better overall in terms of accuracy and computational speed between polynomial regression and simple decision trees when it comes to predicting medical insurance prices? So this question aims to determine the balance between model accuracy and computational efficiency in practical application. So question two, does selecting the top three highest correlated features enhance the performance of all the machine learning models as compared to utilizing all of them? So here we seek to understand the impact of feature selection on the performance of machine learning models so that we can evaluate whether a more focused approach can yield better results. And lastly, question three, does the effect of log transformation help improve the accuracy of results? So this question will investigate the role of data transformation technique, especially long transformation, in enhancing model accuracy.
So I will now talk about our methodology. The dataset was sourced from Kaggle and contributed by the user Harish Kumar Data Lab, and it was last updated a year ago. This dataset comprises of 2,772 rows and 7 columns. Each row represents the data of an individual. Among the 7 columns, 6 columns represent independent variables that potentially influence the medical insurance price. These features include age, sex, BMI, smoking status, number of children, and region. The 7th column represents the dependent variable, which is charges. Data preparation is a crucial step in ensuring the accuracy and reliability of our machine learning model by cleaning and transforming the dataset. We began by detecting any columns in our dataset that contain missing values and either removing the rows with missing values or imputing them with appropriate values to ensure the integrity and completeness of our dataset. Then we identify any exact duplicates within our dataset and remove them to prevent redundant data from skewing our analysis and model training. Outliers can significantly impact the performance of our model. We use box plots to identify and visualize these outliers. Once identified, we remove these outliers to maintain a dataset that accurately represents the general population. Next, we use one-hot encoding to convert categorical variables such as sex and region into a binary matrix. This process allows our machine learning model to interpret these categorical features effectively.
We want to examine the effect of feature selection on the performance of our models and its ability to predict the price of medical insurance. So we began by creating a correlation heat map to visualize the relationships between features. Then we generated 3 distinct datasets. The first dataset includes only the features with the highest correlation to the target variable and the target variable itself. The second includes the 3 features with the highest correlations and the target variable, which is charges. And then the last dataset includes all features that show correlation with charges. To normalize the distribution of our dataset, we apply a log transformation to the x variables, which will help in stabilizing the variance. Finally, we split the dataset into training and testing sets using an 80-20 ratio. This ensures that our model can train effectively and its performance can be evaluated on unseen data.
After the data preparation, now we're going to build our models. In this study, we'll use 2 machine learning models to predict medical insurance prices using the provided dataset. Polynomial regression and decision tree models were chosen due to their resilience and flexibility with different dataset conditions and sizes. Both of them uncover underlying patterns without requiring excessive computational power. They are recognized for their better R-squared scores and efficient computation time, making them perfect for our medical insurance prediction tasks. Polynomial regression builds on baseline linear regression, enhancing its capability to handle non-linear relationships. These models induce a regression equation that fits polynomial terms, allowing it to capture the complexity in real-world medical insurance data more accurately. By addressing non-linear patterns efficiently, it ensures precise predictions without excessive computational demands. On the other hand, decision trees suitable for predicting medical insurance prices because of its ability to complex features interactions without needing detailed assumption about the data distribution. It effectively manages nonlinear and non-parametric relationships, making it robust against noise, missing value, and outliers. Moreover, decision trees can be adjusted for deeper insights and stronger predictions. Now we are evaluating our machine learning models to predict medical insurance prices using several key metrics. The table on the right side, they explain their description and also their formula. Firstly, we have mean absolute error, MED, which measure the average differences between predicted and actual values. It gives us a straightforward understanding of prediction accuracy. Next is mean square error, MSE, which calculates the average square differences between predicted and actual value. This metric emphasizes larger errors, helping us understand the model's precisions. Root mean square errors, MSE, is another important metric, providing a quadratic measure of average error magnitude. It's particularly useful for understanding the model's overall performance. We also look at the R-squared score, which tells us how well our model predicts the dependent variable based on the variations of the independent variable. It's a crucial indicator of our model. Lastly is the computational time. It's measured to understand the efficiency of our model. This helps in assessing the model's scalability and feasibility for real-world application. By comparing these metrics, we can visualize and establish which model performs best, ensuring it aligns with our goals and purpose for predicting medical insurance prices. These are the steps that we will follow closely when developing our machine learning models to ensure the best prediction of medical insurance prices. As seen in the table beside the methodology summary, it lists the details of each models, including the feature selection, log transformation, and the specific data frames used. For example, polynomial regression was tested with 1 feature, 3 features, and all features, both with and without log transformation. Similarly, the decision tree models was evaluated under the same conditions to ensure a comprehensive comparisons. By following this thorough methodology and referencing the details table, we ensure that our models are robust, accurate, and reliable for predicting medical insurance prices.
Now let's move on to our results forecast. So in the first experiment 1A, we actually using a polynomial regression models with a single feature smoker yes and another log transform target variable charges log. This model show a moderate fit with R-square values of 0.231 for training sets and 0.185 for testing set. The aerometric MAE and RMSE in these models were low, indicating decent predictive accuracy. In the meantime, the computational times was a little bit higher, which is at 0.0469 seconds, but is still considered efficient. Moving on to the next experiment 2B, we use the smoker yes fixtures, but this time with the original charges target variables in the polynomial regression models. And overall, this model achieved R-square values of 0.375 for training set and 0.267 for testing set. This error metric were higher compared to the log transform model just now due to the larger scale of the charges variables. And the computational time was efficient, which is at 0.0217 seconds. In experiment 1C, we expanded our features to include smoker yes, age, and BMI with a log transform charges log target variables. This model performed well with a R-square value of 0.737 for training sets and 0.64 for testing set, showing a very good fit. The aerometric MAE and RSE were low, indicating good predictive accuracy. The computational time was efficient, which is at 0.031 seconds only. In experiment 1D, we use the feature smoker yes, age, and BMI like just now, but this time with the original charges target variable. This model achieved R-square value of 0.636 for training set and 0.533 for testing set. Similar to experiment 1B, the error metric here were higher compared to the log transform model due to the larger scale of the charges variables. In the meantime, the computational time was efficient, which is at 0.0355 seconds. Now in experiment 1E, we included all the features with a log transform charges log target variables. This model performed the best among all the experiments with R-square value of 0.796 for training sets and 0.671 for testing set. The low aerometric MAE and RMSE indicates excellent predictive accuracy in these models. The computational time was 0.09 seconds, making it efficient given the complexity. Overall, this model demonstrated the strongest performance across all the experiments. In the last experiment in polynomial regression models, 1F, we included all features with the original charges target variables. This model achieved R-square values of 0.661 for training set and 0.556 for testing set. While these values are reasonable, but the error metric was once again higher due to the larger scale of the charges variable compared to the log transform models. In the meantime, the computational time was 0.1 seconds, making it efficient given the complexities. In experiment 2A, now we are using a decision tree regression models with the smoker yes features and log transform charges log target variables. This model had moderate R-square values of 0.231 for training and 0.183 for testing set, indicating it captures some variance but still has the room for improvement. The model performed well with low metric MAE and RMSE, showing decent predictive accuracy. It was also computationally efficient, taking just 0.02 seconds to run. Moving on to our experiment 2B, now we use the smoker yes features and the original charges target variables. In this model, the R-square value is 0.376 for training sets and 0.262 for testing set. Once again, the error metric were higher due to the larger scale of the charges variables. In the meantime, the computational times were efficient, which is at 0.0213 seconds. Moving on to our experiment 2C, now we expanded our features to include smoker yes, age, and BMI with a log transform charges log target variables. Overall, this model performed very well on the training data with an R-square value of 0.987, but the testing set of R-square value dropped to 0.416, indicating some overfitting happened here. The training error was very low, but the higher testing error suggests that the model could benefit from regularizations. Computational time was again efficient at just 0.0199 seconds. In experiment 2D, we use the feature smoker yes, age, and BMI with the original charges target variables. This model achieved a higher value of R-square value of 0.986 on the training sets, but only 0.27 on the testing set, indicating significant overfitting. Despite the high training accuracy, the large difference in the test performance shows the model struggles to generalize to the new and unseen data. The computational time was very efficient at just 0.0166 seconds. In experiment 2E, we included all the features and used a log transform charges log target variables. This model, which is the best in the decision tree regression models, performed exceptionally well on the training set with an R-square value of 0.996 and also show a moderate good fit on the testing set with an R-square value of 0.527. Both training and testing error were low, indicating a strong predictive performance in these models. The computational time was efficient at just 0.018 seconds. In our last experiment, we used all the features with the original charges target variables. In this model, it achieved a high R-square value of 0.996 on the training set, but only 0.132 on the testing set, indicating the most significant overfitting across all the experiments. Despite the high training accuracy, the large difference in the test performance showed the model struggles to generalize to new and unseen data, and the computational time was efficient at 0.0173 seconds only.
Next, I will be talking about the analysis and recommendations. For the experimental analysis, we have the scope of research and the overall result, where we compared the performance of polynomial regression and decision tree models with different number of correlated features and found that the polynomial regression model is the overall best performing model. Although the computational time was higher in polynomial regression than decision tree, accuracy is a much more important metric for us to consider, and the CT time was negligible as both models were still relatively fast. 3 separate datasets were created after visualizing the relationships. They were the first dataset, which is highly correlated features only, second dataset, 3 highly correlated features, and the third dataset, which is all correlated features, which gave us the best performance. And we concluded from our experiments that using log transformation on both models improved the accuracy and lowered error metrics. Talking about the benchmark and related works, we have 4 different experiments for related work results, 2 of which are highlighted, which are the foot experiment and the Al-Balawi experiment. These 2 experiments are highly consistent with our own models that were used in our study, which will be discussed in the following slide. For the models built in this study, we have 2 different experiments conducted for 2 models. The first model is the polynomial regression test, and the second model is the decision tree test. Results we get in these 2 experiments are relatively consistent with the benchmark results that were highlighted in the previous table. Both experiments have lower R-squared score and higher RMSE compared to the related works results done by Al-Balawi and Fortson-Reiter respectively. Some limitations that we faced in our project was the model performance, where the decision tree model had overfitting issues, where the training errors were much lower than the testing errors. The quality of data, where the presence of outliers and duplicate rows in the dataset initially could have impacted the performance of the model. The feature selection, where due to one hot encoding, the dimensionality of the dataset was increased. And the last one is the complexity of the model, such as polynomial regression, which could increase with the degree of polynomial, potentially leading to overfitting. Some recommendations for our project would be feature engineering, where we can consider doing PCA, which is principal component analysis, to reduce the number of dimensions in the dataset. The second one would be hyperparameter tuning techniques such as grid search or random search in order to find the optimal parameters of the models. And the third one would be increasing data size using data augmentation, which is the process of artificially generating new data from existing data and is a technique to train ML models, as having a larger data set can provide better results and improve model generalizability. Moving on to the social impacts that we will face. The first one is the fair pricing. We are accurately predicting the medical insurance prices could lead to a more fair pricing standard set for medical insurance pricing, which would potentially lower the cost and increase affordability for consumers. And the second one is risk management, where insurance companies can offer better coverage plans based on the individual needs with an accurate model prediction. Secondly, the ethical issues that we would face is the first one being data privacy. As the dataset viewers will contain sensitive information on patients, it is vital to ensure that the patient's information is protected and privacy laws and ethical standards are followed. The second one is transparency. In order to make sure the stakeholders understand the workings of the model, it is important for the model to be interpretable and transparent. Lastly, I'll be talking about the conclusion. In conclusion, we were able to develop a reliable machine learning model that accurately predicts the insurance prices, fulfilling our research objectives. Initially, we conducted data preprocessing and EDA on the dataset. We then conducted 5 experiments each on 2 different machine learning models, namely polynomial regression and decision tree model. Analysis showed that the overall best performing model was polynomial regression, and from polynomial regression, we found that polynomial regression models with log transformation showed the best performance metric values with the highest R-squared score values and the lowest error metric values, namely MSE, MA, and RMSE values, for both training and the test set. Thank you.